antennas, problems on dipoles and loops, series on antennas and wave propagation, lecture number 2.16. In the present session, we consider some problems and their solutions. Problems being set on radiation resistance, loss resistance, directivity, effective length, etc. of straight dipole antennas and also loop radiators. To begin with, we consider a problem. Example 1. Calculate the radiation resistances of lambda by 16 and lambda by 2 wire dipoles in free space. They are radiating in free space. What is the radiation resistance when lengths are lambda by 16 and lambda by 2? Solution. The first dipole length is lambda by 16. It is less than lambda by 10. So it can be considered as an elementary dipole. For elementary dipole, radiation resistance is given by this formula 80 pi square dl by lambda whole square. Given that dl is lambda by 16, substituting this value for dl, one can get radiation resistance as 3.09 ohms. Notice it is very small. When the length is lambda by 2, second part, the dipole becomes half-wave dipole. For half-wave dipole, radiation resistance is constant, 72 ohms. Another problem, example 2. An elementary dipole of length 3 meters, radius 1 mm is radiating at 1 megahertz. Find radiation efficiency. If the radiating conductor is non-magnetic and has a conductivity equal to 57 into 10 power 6 moles per meter. So elementary dipole is given, its length is given, its radius is given, frequency of operation is given. We are asked to find radiation efficiency. Radiation efficiency is total radiated power over input power. Input power to the radiator, it gets split into two parts. One part is radiated power, another part is loss power. And radiation resistance is a quantity proportional to radiated power, whereas loss resistance is a quantity proportional to loss resistances. Now we need to have radiated power and losses power, or radiation resistance and loss resistance to compute radiation efficiency, either this or this. We try to evaluate radiation efficiency using the second formula, which requires radiation resistance and loss resistance. How radiation resistance is computed, how loss resistance is computed, we see in the solution. From the given data, wavelength corresponding to the frequency 1 megahertz is 300 meters, C by F. Radiation resistance, it can be computed using the formula R radiation is equal to 80 pi square dl by lambda whole square. Because it is given that the dipole is an elementary one, so we can safely use this relation. L is 3 meters, lambda is 300 meters, dl is L, therefore 3, lambda is 300. It gives radiation resistance as 0.079 ohms. Radiation resistance is available. Now we go for loss resistance. What is loss resistance? This is dipole. As it is working at high frequencies, the currents in the dipole, they are concentrated near to the surface. A small thin layer near to the surface. Currents exist only in this layer, outer surface layer. Currents flow parallel to the length. Like these currents gives rise to ohmic losses or copper losses or I square R losses. The resistance corresponding to these losses is R loss. It can be computed using the formula given here. R loss is length of the conductor dipole by conductivity into area, cross-sectional area. Here the area is area of this thin layer, this layer. Area of this layer can be found by multiplying the circumference of the conductor with the thickness of the layer. Thickness of the layer is given by skin depth, delta. L by sigma A is a standard formula for resistance of a conductor. To use this formula in the present context, we have to substitute 3 meters for capital L, 57 into 10 power 6 for sigma conductivity, and 2 pi A into delta for area. A is given, small a is given, it is a radius 1 mm, and delta is required. We need to find its value. Skin depth delta can be determined using this formula 1 over square root of pi f mu sigma. F is frequency, it is given. Mu is permeability of a free space because it is non-magnetic. Sigma is given, conductivity 57 into 10 power 6 moles per meter. Substituting the given values, one can determine delta. It comes out as 1 over 15 mm. So delta is available. Substituting delta in the expression for loss resistance, one can get it as 0.126 ohms. So now radiation resistance is available, loss resistance is available. When both the things are available, radiation efficiency can be determined from this formula, R radiation over R radiation plus R loss. In the present case, this efficiency turns out to be 38.54%. Another problem, example 3. An elementary dipole of length 0.01 meters is radiating a power of 100 watts at 100 megahertz. Find A. Current. B. Magnitude of electric field E. C. Magnitude of magnetic field H at a distance of 50 meters in theta equal to 45 degrees direction. This is the problem. We are asked to find out current and also fields, electric field and magnetic field at a distance of 50 meters at a direction given by theta equal to 45 degrees. 45 means this is theta, 45. Here in this direction at a distance of 50 meters, we are asked to find current and fields. Solution. From the given data, wavelength can be determined. It turns out to be 3 meters. Radiation resistance also can be determined. It is given that it is elementary dipole. Therefore, we can use the formula R radiation is 80 pi square dl by lambda whole square without any hesitation. Substituting the available values for length and wavelength, one can obtain radiation resistance as 8.80 milliohms. Now a part of the problem. If I is current amplitude, it can be found from radiated power P radiated and radiation resistance or radiation as P radiation or radiated power is equal to half I square. I is the current amplitude into radiation resistance. Radiated power is half I square into radiation resistance. Now radiating power is available. Radiation resistance is available. Current can be determined without any difficulty. In the present case, it turns out to be 151 amperes. This is superfluous. B part. Electric field magnitude. It can be determined using the formula E equal to 60 pi I dl sin theta by lambda r. This is expression for a radiation field due to elementary dipole radiation. I is available, dl is available, theta is given as 45 degrees, lambda wavelength is available, distance is given, r is available, 50 meters. Substitution gives us E as 1.34 volts per meter. C, here magnetic field is determined. H is equal to half ideal sin theta by lambda r. This is also a standard formula for magnetic field due to elementary dipole radiation. Substituting the available values for all the quantities that are there in this expression, one can obtain H without any difficulty. In the present case, it turns out to be 3.56 milliamperes per meter. Another problem, example 4. Find the radiation resistance of resonant linear electric dipoles of length A, lambda by 50, B, lambda by 4, C, lambda by 2, D, lambda. Different lengths are given. We are asked to find the radiation resistance for each length of the electric dipole. Solution A. In the first case, length is lambda by 50. It is less than lambda by 10. Therefore, the dipole can be considered as an elementary dipole. For elementary dipole, radiation resistance is given by this formula 80 pi square dl over lambda whole square. Dl is lambda by 50. Substitution gives us radiation resistance as 0.312 ohms. B. Length of the dipole in this case is lambda by 4. It is not less than lambda by 10. In fact, it is more than lambda by 10. It cannot be a true elementary dipole, and the formula for radiation resistance of elementary dipole cannot be used here to find radiation resistance. But in the absence of any other formula, we use the formula of elementary dipole to find the radiation resistance of lambda by 4 dipole. Substituting lambda by 4 for dl, we get radiation resistance 48.79 ohms. But it has to be noted that this result is far from exact one. Considerable error exists in this result. C. Length in this case is lambda by 2. When length is lambda by 2, dipole is half wave dipole. For half wave dipole, radiation resistance is 72 ohms. D. In this case, length is 1 lambda, 1 wavelength. In such case, radiation resistance is given by a formula 73 plus 69 log n. N is number of half wavelengths. 1 wavelength means 2 half wavelengths. So n equal to 2. Substitution in this expression gives us radiation resistance as 93.77 ohms. Another problem, example 5. A thin dipole is lambda over 15 long. If it has a loss resistance of 1.5 ohms, calculate its A, directivity, B, effective aperture, C, beam solid angle, D, radiation resistance, E, gain. The dipole length is lambda by 15. It is less than lambda by 10. Therefore, the given radiator can be considered as an elementary dipole, and we can use the expressions that are available for elementary dipole to calculate the required parameters. Solution. The given dipole has length lambda by 15, which is less than lambda by 10, so it can be considered as an elementary dipole. Relations derived earlier for various quantities pertaining to elementary dipole can be used to find their values for the given dipole. For the dipole on hand, A. Directivity. First, we find directivity. Directivity of elementary dipole is 1.5. B. Effective area. Effective area is directivity multiplied by lambda square over 4 pi. Wavelength is not available, so we cannot go further regarding effective area. Continuation. C. Beam solid angle. It is 4 pi over D, directivity. In the present case, D is 1.5. So omega A, beam solid angle, becomes 8.381 steradians. D. Radiation resistance. This is standard formula. R radiation is 80 pi square dl over lambda square. dl is the length of the dipole. It is given as lambda by 15. Substitution in this expression gives us radiation resistance as 3.512 ohms. Lastly, gain. Gain by directivity is equal to radiation resistance by total resistance, or gain is equal to radiation resistance by total resistance into directivity. The radiation resistance is available. Total resistance is radiation resistance plus loss resistance. Directivity is 1.5. It gives gain as 1.02. Another problem, example 6. The power gain of a wire antenna is 16 and its radiation resistance and loss resistances are 72 ohms and 8 ohms respectively. What are its A, efficiency, B, directivity? Problem is quite simple. Solution. By definition, efficiency of antenna is ratio of radiation resistance to total resistance. Total resistance means radiation resistance plus loss resistance. Therefore, efficiency is 72, which is radiation resistance, by 72 plus 8. 8 is loss resistance. It gives efficiency as 0.9. B. Gain is product of directivity with efficiency. Hence, directivity is gain over efficiency. It turns out to be 17.778. Notice gain is 16, directivity is 17. Gain is usually smaller than directivity. Not usually, always. Always smaller than directivity, because gain takes losses into account. Another problem, example 7. A half-wave dipole working at 145 megahertz has a loss resistance of 1 ohm. Find its radiation efficiency and effective aperture. This is on half-wave dipole. Solution. Radiation efficiency is equal to ratio of radiation resistance to total resistance. Hence, efficiency is eta equal to 72. 72 is radiation resistance by 72 plus 1. 1 is loss resistance. It gives efficiency as 98.6%. Wavelength corresponding to frequency 145 megahertz is 2.07 meters. So the effective area of the half-wave dipole is, this is standard formula. Effective area is D multiplied by lambda square over 4 pi is a formula valid for any antenna. In the present case of half-wave dipole, directivity is 1.64. Lambda wavelength is 2.07. Substitution and doing a little bit of calculations gives us effective area as 0.559 meter square. Another problem, example 8. A single turn circular loop antenna of 20 centimeter diameter is functioning at a frequency of 100 megahertz. Find its A, radiation resistance, and B, directivity. What happens? See, if this loop is changed into a square one of same area, and D, if number of turns of this circular loop is doubled. A good problem, a standard problem. Solving this kind of problems enhances the understanding of the radiator to a deeper level. Solution. Given the diameter of the loop is 20 cm, 0.2 meters. Area of the loop then becomes 0.031 meters square. Area is pi d square by 4. D is dia. Dia is 0.2 meters. So substitution gives A as 0.031 meters square. The wavelength corresponding to given frequency 100 megahertz is 3 meters. Now lambda square by 100 is 0.09 meters square, as area is 0.031 meters square, which is less than 0.09 meters square, which is lambda square by 100. The loop can be considered as a small one. For a loop to be small one, area, cross-sectional area of the loop must be smaller than lambda square by 100. And this condition is being satisfied here by the given loop. Hence, it is a small one. Once the loop is declared or found a small one, we can use all the formulas that are available for a small loop. A, radiation resistance. Formula for radiation resistance of a small loop is 31.2 multiplied by A by lambda square whole square kilo ohms. Area, we have already computed, 0.031 meter square. Wavelength, it is already found, 3 meters. Now substitution gives radiation resistance of the loop as 0.37 kilo ohms. Directivity of the given loop is 1.5, as is the case for any small loop. See, small loop properties depend only on the area, not on the shape. When it is bent to form a square one while maintaining the area same, properties do not change. Radiation resistance or directivity remains same. D, if the number of turns of the loop is doubled, then the length of the loop conductor becomes 1.2 meters. As the turns times circumference is more than lambda by 10, 0.3 meters, the loop is no more small, and above values for radiation resistance or directivity, they are no more valid when number of turns are doubled. Another problem, example 9. Find the radiation resistance of a 20 turn 1 meter diameter small loop antenna operating at 10 megahertz. If the loss resistance of one turn loop is 1 ohm, find its radiation efficiency. We are asked to determine radiation resistance and radiation efficiency. Solution. Given that number of turns is 20 and diameter of loop is 1 meter, area of the loop then is 0.78575 meter square. Area is pi r square. Diameter of loop is 1 meter, therefore radius becomes 0.5 meters. Area comes out as 0.78575 meters square. Wavelength corresponding to 10 megahertz is 30 meters. Radiation resistance of 20 turn small loop is radiation resistance is equal to 31.2 n number of turns, A by lambda square whole square. This is the formula for radiation resistance. Area is available, wavelength is available, number of turns is available. Substitution gives radiation resistance as 9.5 ohms. If the loss resistance of the one turn loop is 1 ohm, then for the 20 turn loop, it is 20 ohm. Radiation efficiency is the ratio of radiation resistance to total resistance. Radiation resistance is 99.5. Total resistance is loss resistance plus radiation resistance, which is 29.5. This ratio, which is radiation efficiency, in the present case it turns out to be 32.2%. Another problem, example 10. Find the radiation efficiency of A single turn, B 4 turn circular loop, each of radius lambda by 10 pi and operating at 10 megahertz. The radius of the wire is 10 power minus 3 lambda and turns are spaced 3 into 10 power minus 3 lambda apart. Assume the wire is copper with conductivity of 5.7 into 10 power 7 Siemens per meter and antenna is radiating into free space. We are asked to find radiation efficiency. Now, solution. Wavelength corresponding to 10 megahertz is 30 meters. C by F is wavelength. Radius of the loop is D by 2. This D by 2 is given as lambda by 10 pi. Lambda is 30 meters. Therefore, D by 2 becomes 0.96 meters. D is diameter of the loop. Radius of the wire is given as 10 power minus 3 lambda. When lambda is 30 meters, it becomes 0.03 meters. Spacing of the wire is given as 3 into 10 power minus 3 lambda. When lambda is 30 meters, it becomes 0.09 meters. These quantities are required for us to calculate radiation efficiency. Now we consider the case of single turn circular loop. The circumference or length of a single turn loop becomes L is 2 into pi into radius. Radius is 0.96. So length becomes 6 meters. Ohmic or loss resistance. It can be obtained from this formula. Resistance is resistivity multiplied by length divided by cross-sectional area. Conductivity is given, which is inverse of resistivity. Length is available, conductivity is available, cross-sectional area is available. Substitution gives us loss resistance as 0.037 into 10 power minus 3 ohms. The radiation resistance of single turn small loop is, this is standard formula for radiation resistance. Area is available, lambda is available. Substitution gives us radiation resistance equal to 100 ohms. As radiation efficiency is a ratio of radiation resistance to total resistance being radiation resistance plus loss resistance. Efficiency becomes 100 by 100 plus 0.037 into 10 power minus 3. Roughly, it is 100%. Second part, B part of the problem. 4-turn circular loop. In this case, length is 4 times square root of pi d square plus s square. It comes out as 23.99 meters. This is length. Once length is available, ohmic loss resistance can be computed. It turns out to be 0.148 into 10 power minus 3 ohms. Radiation resistance of 4-turn small loop is 31.2 into 4a by lambda square whole square. Using this formula, radiation resistance can be obtained. It turns out to be 1600 ohms. Then radiation efficiency can be determined within no time, as it is radiation resistance by total resistance. It turns out to be 99.99%. Notice here S is turn spacing, which we have already calculated and found it equal to 0.09. Now we come to an end to the session. To recap, in the session we considered, we solved, we described several problems and their solutions. The problems being set on dipole antennas, loop antennas, their radiation resistances, loss resistances, and efficiencies. Hope this session is useful to you. We meet again in another session with a new topic soon.